This video will explain the concept of DECbit and how it functions. Let's begin by exploring the fundamentals of DECbit. DECbit is indeed a router-based congestion avoidance scheme. DECbit or Destination Experiencing Congestion Bit is a congestion notification mechanism used in routers to help avoid network congestion by providing feedback to the senders. So actually, a DECbit is a congestion control technique implemented in routers to avoid congestion. Okay. Each router actively monitors its traffic load and sends explicit notifications to the end nodes when congestion is imminent. That is, each router monitors the load it is experiencing and explicitly notifies the end nodes when congestion is about to occur. This notification is executed by inserting a binary congestion bit into the packets that pass through the router, thus leading to the term DECbit. Actually, this notification is accomplished by inserting a binary congestion bit into the packets as they pass through the router, giving rise to the name DECbit. Therefore, it is named DECbit. Okay. The destination host subsequently copies this congestion bit into the acknowledgement ACK it transmits back to the source. Finally, the source adjusts its transmission rate so as to avoid congestion. This means the destination host then copies this congestion bit into the ACK it sends back to the source. Ultimately, the source adjusts its transmission rate to proactively prevent congestion. Okay. Next, we will explore the inner workings of DECbit within a network. Figure 1 shows a simplified overview of a network. In Figure 1, the sender is a device or system that is transmitting data packets to a receiver over a network. And routers A and B are intermediate routers in the network path between the sender and the receiver. Routers are responsible for forwarding data packets to their destination. Also in Figure 1, the receiver is the endpoint that receives the data packets from the sender. Okay. Data transmission. The sender is transmitting data packets to the receiver. These packets may traverse several routers in the network, such as router A and router B. That is, the sender is sending data packets to the receiver, and these packets may pass through multiple routers within the network, including router A and router B. Congestion detection. Router A or router B or any other router in the network may detect congestion on its outgoing links. This congestion could occur due to network traffic exceeding the available capacity, leading to potential packet loss. That is, a router A or router B or any other router within the network might identify congestion on its outbound links. This congestion could result from network traffic exceeding the available capacity, potentially resulting in packet loss. Okay.
Setting DECbit. For example, when router A or any router detects congestion, it sets the DECbit in the IP header of the packets that pass through it. The DECbit indicates that the destination, that is the receiver, is experiencing congestion. Okay.
For instance, when router A identifies congestion, it sets the DECbit in the IP header of the packets passing through it. The DECbit indicates that the destination, that is, the receiver, is encountering congestion. Packet forwarding. The DECbit marked packets continue to be forwarded to router B and ultimately to the receiver. Here, packets marked with the DECbit are forwarded to router B and finally reach the receiver. Receiver's role. When the DECbit marked packets arrive at the receiver examines the DECbit and understands that there has been congestion along the network path. That is, once these DECbit marked packets arrive at the receiver examines the DECbit. If the DECbit is set, it understands that there has been congestion along the network route. Okay. Receiver feedback. The receiver can use the information provided by the DECbit to adapt its behavior. For example, it may send feedback to the sender, informing it that congestion has been detected during transmission. That is, the receiver can utilize the information conveyed by the DECbit to adjust its behavior. The receiver may, for example, inform the sender about the congestion it has detected by sending feedback. Okay. Sender's reaction. Upon receiving feedback from the receiver regarding congestion, for example, through acknowledgements or specific feedback packets, the sender can react by reducing its sending rate or taking other congestion control measures. This helps prevent further congestion in the network. That is, once the sender receives feedback from the receiver regarding congestion, for example, through acknowledgements or specific feedback packets, it can react by reducing its sending rate or taking other congestion control measures. In brief, DECbit is part of a congestion avoidance mechanism in routers. It allows routers to provide feedback about congestion conditions to the sender indirectly via the receiver, helping to improve congestion control and network efficiency. This means DECbit is a component of a congestion avoidance mechanism in routers, enabling routers to indirectly convey feedback on congestion conditions to the center through the receiver. This contributes to enhanced congestion control and overall network efficiency. Okay. Moreover, please note that this diagram, or that means figure 1, and explanation provide a simplified overview of how TechBit operates in a network. In a real world scenario, there may be more routers and a more complex network topology, but the fundamental principles remain the same. Okay. Next, we will explore the algorithm outlining the operation of TechBit, specifically focusing on how congestion is determined and how the congestion indication bit is set in the packet header. A single congestion bit is added to the packet header. When a packet arrives at the router calculates the average queue length over a time interval that spans the last busy plus idle cycle plus the current busy cycle. The router is busy when it is transmitting and idle when it is not. If the average queue length is greater than or equal to 1, then the router sets the congestion indication bit in the packet header of arriving packets. As mentioned earlier, a single congestion bit is added to the packet header. The router sets this bit in a packet if its average queue length is greater than or equal to 1 at the time the packet arrives. Okay, let's describe how to graphically represent the computation of the average queue length at a router in the context of TechBit congestion management. Figure 2 shows the queue length at a router as a function of time. Time is represented on the horizontal axis starting from t equal to 0 and extending to a certain time period. The vertical axis, that is y-axis, represents the queue length, showing how many packets are waiting in the router's queue at different points in time. Okay. At the beginning, t equal to 0, the queue length is typically 0, as no packets have arrived yet. That is, the queue length is initially 0 because no packets have arrived at that point in time. As packets arrive at the router, the queue length increases. The graph will show an upward trend in the queue length. When packets reach the router, the queue length increases, resulting in an upward trend on the graph. Okay. When packets are processed and leave the queue length decreases. This is represented as downward trends in the graph. As packets are processed and leave the queue, the queue length decreases, indicating a downward trend on the graph. Okay. The queue length may fluctuate over time as packets continue to arrive and depart. The queue length may fluctuate over time because packets continue to arrive and depart. To compute the average queue length, you would calculate the area under the curve on the graph and divide it by the time period. This area represents the total work done by the queue over time. That is, to compute the average queue length, the area under the curve on the graph would be calculated and it would be divided by the time period. This area represents the cumulative queue length over the observed time period. Okay. Furthermore, if the average queue length is greater than or equal to 1, then the router sets the congestion indication bit. This presents a compromise between substantial queuing, resulting in higher throughput and increased idle time, leading to lower delay. That is, using a queue length of 1 for setting the congestion bit is a trade-off between significant queuing, which can lead to higher throughput, and increased idle time, which can result in lower delay. Okay. In other words, a queue length of 1 appears to optimize the power function. The source tracks packets that trigger router congestion bits and monitors the congestion window's effectiveness, similar to DECbit. That is, the source records how many of its packets resulted in some router setting the congestion bit and maintains a congestion window just as in TCP. If less than 50% of packets have the congestion bit set, the source increases its congestion window by 1 packet to make better use of available bandwidth. Say, if less than 50% of the packets have the congestion bit set, it leads to an increase in the congestion window for better bandwidth utilization. Okay. If 50% or more packets have the bit set, the source decreases its congestion window to 0.875 times the previous value to alleviate congestion without causing instability in the network. Suppose if 50% or more of the packets have the congestion bit set, the congestion window is reduced to 0.875 times the previous value to alleviate network congestion. Okay. The choice of a 50% threshold in DECbit is based on empirical data, indicating that it corresponds to the peak congestion point. Say, in DECbit, the 50% threshold indicates when to adjust congestion control. Okay. The increase by 1, decrease by 0.875 rule is adopted for stability with additive increase for network probing and multiplicative degrees to prevent aggressive congestion growth. This means that if 50% or more packets are marked, the congestion window decreases by 0.875 times its previous value to alleviate congestion. If fewer packets are marked, it increases by 1 for better bandwidth use. This explanation is clear and effectively conveys how DECbit's congestion control mechanism operates in response to the 50% threshold. By monitoring this average queue length, network administrators can assess congestion levels and make informed decisions to manage network traffic effectively. The DECbit and other congestion management mechanisms help in controlling congestion and maintaining a reasonable queue length to ensure smooth data flow. In conclusion, network administrators can effectively manage network traffic by monitoring the average queue length, enabling them to assess congestion levels and make informed decisions. Utilizing mechanisms like the DECbit and other congestion management techniques, they can control congestion and maintain a manageable queue length, ensuring the smooth flow of data. Okay.